Hello, my name is Caitlin Miley, and today I'll be presenting the work of myself and my co-authors on when, where, and how to add neurons to artificial neural networks. In conventional deep learning, the standard process for finding the right model is to hand engineer a static architecture from off-the-shelf examples that worked well in other problems, train its parameters on the specific task, and repeat until satisfied with the performance. This isn't a very informed process, neither for why certain types of structures help or hinder a given task or dataset, nor for whether other architectures could be better than the current one. So we can instead use structural learning to automate the architectural optimization process. Structural learning is the process of optimizing both the architecture and its parameters of a neural network. Considering the operations we can perform on the graph structure of a neural network, pruning from a neural network is well studied, but adding to it is not. Many works use pruning of connections, neurons, or even higher structures as a method for compression, and this is relatively easy because the search space of entities to prune is finite, like in this example of neural pruning. On the other hand, trying to add new entities has an infinite search space, even if we only consider widening existing layers with new neurons. In order to tackle this larger search space, we break neurogenesis down into the following considerations. The first dimension to consider is when a new neuron is added. Because we are considering neurogenesis during the gradient descent process, this is discretized by the weight update steps. Because of this discretization, we should also consider how many neurons to add at a given time. Next is where or which layer to add to. Finally, we should consider how, which is the initialization of the new neuron. We can answer these first two questions with a single trigger function, which is evaluated on each layer at each step and outputs the number of neurons to add, whether it's 0 or more than 0. Then we can use an initialization function on each layer that has at least one new neuron to initialize. Thus, a neurogenesis strategy consists of a trigger and initialization. Previous works in neurogenesis use a predetermined schedule and only propose initialization strategies, so we are the first work to propose dynamic scheduling through the trigger function. Here we present the generic neurogenesis framework, showing how the trigger initialization functions are used within the training process. We see that the neurogenesis steps are baked into the standard training procedure and thus can easily be added within existing training pipelines. Essentially, after each weight update for each layer, the trigger function is evaluated. If the output is greater than 0, the trigger neurons are initialized with the initialization function. We'll now consider how to design a neurogenesis strategy, begin with what information is available in the network. Here we depict a basic multi-layer perceptron zoomed into the Lth layer during a forward pass, with the weight matrices in blue and the pre and post activation matrices in red. In addition to the current weights and activations, the gradients with respect to the weight matrices are also computed during the backwards pass and thus are available to use. Even beyond the information already computed, we can compute an auxiliary gradient, which intuitively represents the potential gradient if neurons from alternating layers were connected. These yield three main sources of information: activations, weights, and gradients. Existing works have only used gradient information thus far, so we propose strategies based on each of these three sources as comparison. Beginning with activations and weights, based on the general goal of an efficient network, we intuitively want each neuron to provide a unique feature rather than be redundant to other neurons. Such uniqueness can be captured by the orthogonality or effective rank of either the activation matrix or the weight matrix. In our setting where we can only add neurons, we propose to add neurons while the orthogonalities are relatively high, as there may be useful neurons not yet present in that layer. When orthogonality is low and thus redundancy is high, we pause neurogenesis and instead continue with just weight updates until the orthogonality increases again. This defines a trigger for activation and weight-based strategies, comparing the current effective rank to a threshold computed by the layer's initial effective rank and a hyperparameter gamma that is near 1. In order to compare our dynamic neurogenesis strategies based on activations or weights to the initializations proposed in previous works, we also designed a gradient-based trigger. The authors of GradMax previously showed that the singular values of the auxiliary gradient matrix are the largest potential gradient norms of new neurons. So we compare these to the gradient norm of the existing neurons to define our gradient-based trigger. Here we summarize the strategies that we will compare empirically. Our North Star strategies based on neural orthogonality consist of activation and weight-based strategies. The main activation-based strategies are North Select, which selects orthogonal neurons from random candidates, and North Pre, which selects orthogonal neurons from candidates that maximize orthogonal preactivations in the multi-layer perceptron case. These are compared to North Random, a baseline which uses a random initialization strategy. North Weight is the weight-based orthogonality strategy. GradMax, Firefly, and Nest from previous works are re-implemented as initializations within a network and paired with the gradient-based trigger. We begin presenting our empirical results on generated data sets. These are simple classification tests with the number of independent features in the dataset varied as shown on the horizontal axes. We grow single layer MLPs in the left plot and 2 hidden layer MLPs in the right plots, comparing final layer widths versus independent features of that dataset, showing the dependency of each strategy on the effective input dimensionality and base architecture. Comparing the first layers across the 2 architectures exhibits the unsupervised nature of North Star strategies, but also the strength of the gradient-based strategies to adapt width to depth. We next show results for 2 hidden layer MLPs for the MNIST classification task. We evaluate the strategies by accuracy in the top plots and training efficiency in the bottom plots, in the fully dynamic setting on the left and in a predetermined schedule setting on the right. The ellipses represent variance and covariance across 2 dimensions, size and either accuracy or training time. For dynamic neurogenesis, the Pareto front of accuracy versus network size is dominated by North Star orthogonality-based methods. As for the predetermined schedule, multiple North Star strategies exceed the performance of the static network of the same final architecture for this task in hyperparameter setting, demonstrating that dynamically growing a network over learning can result in better performance than starting with a network of that maximum final size at initialization. Finally, we show results for deep convolutional networks. These results include the tunable hyperparameter gamma that adjusts the orthogonality threshold for the trigger and activation-based strategies. On VGG, our North Star methods find networks in the same order of size of the standard width network while being competitive or improved in accuracy for both datasets. NorSelect outperforms even the largest static network with less than half as many parameters on both Cypher10 and Cypher100. For wide ResNet, North Star methods tend to grow up to the maximum size, likely due to the complicated dynamics of residual connections on the trigger metrics. Northweight slightly beats the largest static architecture while NorSelect matches performance, and GrabMax beats the static architecture at a similar size. Please see our paper for further analysis such as layer widths and hyperparameter studies. In summary, we present a neurogenesis framework and the North Star suite of neurogenesis strategies composed of triggers and initializations. We are the first work to consider scheduling neurogenesis, as well as to use activations and weights to inform neurogenesis. North Star strategies grow efficient networks which achieve comparable or better performance to static architectures of the same final size across architecture search spaces, tasks, and datasets. We plan to extend beyond dense and convolutional layers and combine our neurogenesis strategies with pruning for dynamic structural learning in future work. Here are the references for the works we compare against. Our code is open sourced. Our paper is accessible on OpenArchive and Open Review and Archive. For any questions, you can contact me by email. Thank you for your attention.